Hi, my name is Joanna Klicka, and today I'm going to be going through Homework 3 Part A. The question states, derive the differential equations governing the rate of change of liquid molar holdup and mole fraction of the more volatile component in a distillation column. Assume constant molar flow rates in each section, negligible vapor dynamics, and a vapor flow to the condenser that is perfectly controlled to match the sum of the reflux and distillate flow. The liquid flow rates can be assumed to follow L equals W times holdup minus holdup naught to the 1.5 power, where holdup naught is the holdup at which no liquid overflows the weir on each stage. This ignores the bubble volume entrained in the liquid. To start analyzing this problem, we are going to draw a picture first. And instead of drawing a whole distillation column, we're going to focus in on one tray. I'm just going to represent this by a rectangle. We'll pretend the rectangle is straight. There we go. And on each tray, you have your vapor flow going up, and you have your liquid flow going down. Now you have your liquid flow from the current tray and your liquid flow from the previous tray, as well as your vapor flow from the previous tray and the vapor flow from this tray. And then this tray is going to have some amount of liquid that has some number of moles. To get our differential equations, we are going to start by doing a mass balance. So if our mass balance, and so we're looking for the change in the number of moles over time. So we have the flows going in. Here's our vapor flow from the tray below, plus our liquid flow from the tray above, minus the flows going out, which is the vapor flow from the current tray, minus the liquid flow from the current tray. Now we also want to look at the mass balance for the more volatile component. What we have here is the overall mass balance. So for that, all we need to do is multiply by the mole fraction of that component. And then we have to carry that on to the right-hand side of the equation as well. So we have yn plus 1 times vn plus 1 plus xn minus 1 times ln minus 1 minus yn times vn minus xn times ln. Now that we have our two mass balances, what we can do is take the overall mass balance and substitute it into the mass balance for the more volatile component. When we do that, what we end up with is x1 times vn plus 1 plus ln minus 1 minus vn minus ln. And then that's going to be equal to the same as the right-hand side of the second equation. And if we carry our mole fraction through, what we end up with is x1 vn plus 1 plus x1 times ln minus 1 minus x1 times vn minus x1 times ln is equal to yn plus 1 times vn plus 1 plus xn minus 1 times ln minus 1 minus yn times vn minus xn minus l.